Welcome to today's problem walkthrough. We'll be exploring problem number 1139, largest one bordered square. In this problem, we'll tackle the challenge of identifying the largest square in a binary grid that is fully bordered by ones. Let's dive into the details and discuss various approaches to solve it. In this problem, you're given a 2D grid made up of cells, where each cell is either a 0 representing water or a 1 representing land. Your goal is to find the largest square that is bordered entirely by 1s. This means that all cells along the edges of the square must be 1, but the inside of the square can contain both 1s and 0s. If no such square exists, you need to return 0. The input will be a 2D list of integers, and your task is to calculate the area of the largest one bordered square as an integer. For example, if the largest square has a side length of 3, the area would be 3x3 equals 9. If no square is valid, the result should be 0. Let's look at an example to clarify this. Here, the grid is a 3 by 3 matrix with 1s on the borders and a single 0 in the middle. In this case, the largest one bordered square is the entire grid itself, because all the edges of the square are 1s. The area of the square is calculated as the side length squared, which is 3x3 equals 9. Therefore, the output for this example is 9. In another example, the grid is a single row with 4 cells. Here, there are no larger squares that satisfy the conditions, but each individual one can be considered as a 1 by 1 square. So, the largest one bordered square has an area of 1x1 equals 1. For instance, we could select cell 0, 0, or 0, 1 as the square. This demonstrates that even small grids can have valid solutions. On the other hand, if the grid contains only 0s, as shown in the next example, there is no valid square, and the output will be 0. In this grid, all cells are 0, meaning there are no 1s to form any square. Since a one-bordered square is not possible here, the output is 0. This highlights an important edge case where the grid contains no land cells at all. Now, moving on to the constraints of the problem, the grid's dimensions will always be between 1x1 and 100x100. The total number of cells won't exceed 10,000, so the solution has to be efficient. Finally, let's discuss a few important edge cases. For a 1x1 grid, the result depends on whether the single cell is a 1 or a 0, giving outputs of 1 or 0 respectively. If the grid has no 1s at all, the output will always be 0. For grids that are just a single row or column, the largest square will be determined by the number of consecutive 1s. And for larger grids, especially close to the maximum size of 100x100, the solution must be optimized to avoid timeouts, ensuring it can handle the problem's constraints efficiently. To approach the problem of finding the largest one bordered square, we can start by considering a brute force solution. The intuition here is simple: iterate over all possible squares in the grid, defined by their top left corner and side length. For each square, check if all its borders consist entirely of ones. To implement this, we loop through every possible starting point, I, j, and test all potential side lengths, k, for squares originating from that point. For each square, we verify its top, bottom, left, and right borders to ensure they're completely filled with ones. While this method is straightforward, it's computationally expensive. The time complexity is O, m*n*, m, n, caret 2, because for each square, verifying its borders takes O, k, and there are O, m*, n*, m, n, possible combinations of I, j, k. This results in many redundant checks, making the brute force approach impractical for large grids. To address the inefficiencies of the brute force approach, we can use an optimized strategy that leverages pre-processing. The key idea is to pre-process the grid to compute the lengths of consecutive ones in each row and column. This allows us to validate the borders of a square much more efficiently. Here's the insight: a square with side length k is valid if its top and bottom rows each have at least k consecutive ones, and its left and right columns also have at least k consecutive ones. To achieve this, we pre-compute two arrays, horizontal I, j, which stores the number of consecutive ones to the left of I, j, including itself, and vertical I, j, which stores the number of consecutive ones above I, j, including itself. With this pre-processing done in O, m*n, time, we can validate squares much faster. By iterating over all possible bottom right corners, I, j, and testing side lengths k from 1 to min, I, j, plus 1, we check the validity of a square in constant time using the pre-computed arrays. For example, we confirm the bottom row of the square has enough ones by checking horizontal, I, j, k plus 1 equals k. Similarly, the top row, left column, and right column can be validated using their respective conditions. This significantly reduces the computational overhead compared to brute force. Overall, the optimized approach achieves a time complexity of O(m*n*min, m(n), which is a substantial improvement over the brute force method. This efficiency comes from avoiding repetitive border checks and leveraging the pre-computed horizontal and vertical arrays for rapid validation. The advantages of this approach are clear: it scales well for larger grids, eliminates redundant computations, and is computationally feasible for real-world scenarios. Therefore, we chose the optimized pre-processing strategy as our solution. It balances efficiency, scalability, and clarity, making it ideal for this problem. While the brute force method may be simpler conceptually, its computational expense makes it impractical for larger inputs. In contrast, the optimized approach requires slightly more pre-processing effort but is significantly faster and more scalable. This trade-off ensures that our solution is both effective and maintainable, highlighting the importance of leveraging pre-processing to simplify complex problems like this one. The problem requires us to find the largest square subgrid in an MXN binary grid, where the borders of the square are composed entirely of ones. If no such square exists, we return 0. To start, we can use a brute force approach. The idea is to examine every possible square in the grid by identifying its top left corner and side length. For each square, we check if its borders are completely filled with ones. To implement this, we initialize a variable, max_side, to track the side length of the largest valid square we find. We then iterate over all potential top left corners of squares using 2 nested loops, one for rows and one for columns. Each cell in the grid is treated as a potential starting point for a square. Once we have a top left corner, the next step is to explore all possible side lengths for the square. The maximum possible side length is determined by ensuring the square fits within the grid. For a given square, we validate its borders by checking if all the cells along the top, bottom, left, and right edges are ones. Specifically, the top border is checked by iterating through the columns from the top left corner, the bottom border by iterating through the columns at the bottom row of the square, and similarly for the left and right borders using their respective rows. If all these checks pass, the square is valid, and we update max_side to the larger of its current value or the side length of this square. Finally, after evaluating all possible squares, we return max_side as the result. Analyzing this brute force approach, we see it involves iterating over every possible top left corner and every possible side length. For each square, validating the borders takes time proportional to the side length. This results in an overall complexity of O(m*n*min, m(n)(2), which can be computationally expensive for large grids. To optimize this, we noticed that repeatedly checking borders is redundant and could be streamlined. By using dynamic programming, we can pre-compute auxiliary data structures, which allow us to validate borders more efficiently. This significantly reduces the overall computational cost of the solution. To implement an optimized approach, we rely on additional data structures. The grid itself remains the primary input, but we introduce auxiliary arrays for prefix sums along rows and columns. These prefix sums allow us to quickly check if a segment of a border contains only ones, reducing the cost of border validation to O(1). The core of the optimization lies in dynamic programming. We define a DP table where each cell represents the side length of the largest square ending at that cell, with all borders containing only ones. By building this table iteratively, we can efficiently compute the solution while avoiding redundant checks. The transition relation of the DP table is based on the dependencies of the square ending at a given cell. For a square to end at I, j, the cell itself must contain a 1, and the row and column segments forming its borders must also be valid. Additionally, the square relies on the largest square ending at I1, j1. This gives us the relation dp I, j equals min dp I1, j dp I, j1 dp I1, j1 plus 1, provided the borders are valid. For the first row and column, the base case is simple: any cell containing a 1 forms a square of size 1. Optionally, prefix sums can be used to validate borders more efficiently. During the computation, we track the maximum value in the DP table, which corresponds to the side length of the largest valid square. Once the DP computation is complete, we return either the side length or the area of the largest square, depending on the problem requirements. The time complexity of this optimized approach is O(m*n), as we compute the DP table in a single pass and optionally calculate prefix sums in another pass. The space complexity is also O(m*n) due to the DP table, though it can be reduced with optimizations. Finally, handling edge cases is crucial. For example, if the grid is entirely zeros, we return 0, while a grid with a single 1 results in a square of size 1. For non-square grids, careful bounds checking ensures correctness. This approach ensures efficiency even for large grids, making it a significant improvement over the brute force method. Here, we start by defining the class and the method largest one bordered square, which takes a 2D grid as input. The first step is to calculate the dimensions of the grid, m and n, representing the number of rows and columns, respectively. Next, we initialize two 2D arrays, horizontal and vertical, both of the same size as the grid, to store cumulative sums of ones along the rows and columns. These arrays help us efficiently determine how many consecutive ones exist up to a given cell, either horizontally or vertically. Now, using nested loops, we iterate through every cell in the grid. If the current cell contains a 1, we update the horizontal and vertical arrays. For horizontal I, j, it adds 1 to the value from the previous column if there's a 1 there, or sets it to 1 if it's the first column. Similarly, vertical I, j, checks the value from the previous row and updates accordingly. This pre-processing ensures we can quickly calculate the boundaries of any potential square. Then, we initialize max_side to 0, which will keep track of the largest square side length found so far. Now we move to the part where we analyze possible square sizes at each grid cell. To determine the largest square, we iterate through each cell in the grid again. For each cell, we consider the largest possible square that could end at that position, starting with the smaller of the horizontal and vertical values for that cell. While the potential side length is larger than the current max_side, we check if the top and left boundaries of the square also have sufficient consecutive ones to form valid borders. This is done by verifying values in the horizontal and vertical arrays for the appropriate starting positions of the square. If the square is valid, we update max_side to this new side length and exit the loop to avoid unnecessary checks for smaller squares. Finally, when all cells have been processed, the largest square's area is calculated by squaring max_side, and the result is returned. This entire approach ensures we efficiently handle the grid and calculate the largest one bordered square with minimal computational overhead. Here, we start by defining the largest one bordered square method, which takes a 2D grid as input. The grid represents a binary matrix of zeros and ones. First, we extract the dimensions of the grid, M4 rows and N4 columns. To optimize the process of checking square borders later, we pre-compute two auxiliary matrices, horizontal and vertical. These matrices will store cumulative sums of consecutive ones horizontally and vertically, respectively. Now, as we loop through each cell in the grid, if the cell contains a 1, we update the horizontal matrix by adding 1 to the value of the cell to its left, or just 1 if it's the first column. Similarly, we update the vertical matrix by adding 1 to the value of the cell above it, or just 1 if it's the first row. This pre-processing step allows us to quickly check the length of horizontal and vertical lines of ones at any given cell. Finally, we initialize max_side to 0, which will keep track of the largest square size we find. Next, we iterate over each cell in the grid again to evaluate all possible square sizes. For each cell, we calculate the potential side length of a square by taking the smaller value between the horizontal and vertical cumulative sums at that cell. Then, we check if a square of this size, with the current cell as its bottom right corner, has valid borders. Specifically, we verify that the top border has enough horizontal ones and the left border has enough vertical ones to form a complete square. If the square is valid, we update max_side to the current side length and break out of the loop to maximize efficiency. If the square is not valid, we decrement the side length and check again until no larger square can be formed. Finally, we return the area of the largest square, which is max side squared. To solve the problem, we start by pre-computing two helper arrays, horizontal and vertical. These arrays allow us to efficiently determine the count of consecutive ones in the grid. The horizontal array tracks how many ones appear consecutively from the left for each cell. Similarly, the vertical array tracks the count of consecutive ones from above for each cell. For the given input grid, we calculate these values for every cell. In this case, the horizontal array shows the cumulative count of ones row-wise, such as 1, 2, 3, across each row, and the vertical array accumulates the count column-wise, such as 1, 2, 3, down each column. These pre-computed arrays will help us efficiently verify the borders of potential squares in the next steps. Now, we iterate through each cell in the grid to determine the largest possible square that can have that cell as its bottom right corner. For example, at cell 2, 2, the bottom right corner of the grid, we calculate the maximum possible side length for a square by taking the smaller value between horizontal 2, 2 and vertical 2, 2. Here, the side length is 3. Next, we check if the top border and left border can support a square of size 3. Specifically, we verify if the horizontal array at the top row and the vertical array at the left column have at least 3 consecutive ones. Since both conditions are met, we confirm that a valid square exists, and we update the max_side to 3. With this, the area of the largest square is 3*3 equals 9. Moving to another example, we consider a non-square grid to explore more complex scenarios. In this new example, we repeat the same process of pre-computing the horizontal and vertical arrays. For this grid, the horizontal array reflects the count of consecutive ones for each row, while the vertical array does the same for each column. After pre-computing, the arrays capture patterns of ones, such as 1, 2, 3, 0 in the horizontal array and 1, 2, 1, 0 in the vertical array. Next, we begin iterating through the grid to find the largest square. At cell 1, 2, the bottom right corner of a potential square, we calculate the maximum side length as 2, which is the smaller value between horizontal 1, 2 and vertical 1, 2. To verify the square, we check the top and left borders for at least 2 consecutive ones. The top border at horizontal 0, 2 satisfies this condition, so we proceed to the left border. The left border at vertical 1, 1 also satisfies the condition for a square of side 2. Thus, we confirm a valid square at this location and update the max_side to 2. Later, at cell 2, 3, we compute the maximum side length as 1. Since there is only one consecutive one in both the horizontal and vertical directions. A square of side 1 is valid, but it doesn't exceed the current max_side, so no update is made. With these results, the largest square in this grid has an area of 2*2 equals 4. Finally, we turn to an edge case where the grid does not contain any larger valid square beyond single-cell squares. In this edge case, we start again by pre-computing the horizontal and vertical arrays. Here, the arrays are quite sparse, with most values being 0 due to the lack of consecutive ones. For instance, the horizontal array for the first row is 1, 0, 1, and the vertical array is the same, given the isolated ones in the grid. As we iterate through the grid, we find that only single-cell squares of side 1 are possible at positions like 0, 0, 0, 2, 2, 0, and 2, 2. These squares are valid, but since no larger squares can be formed, the max_side remains 1. After completing the iterations, the final result for this edge case is simply the area of the largest square, which is max_side asterisk max_side equals 1. This demonstrates that even in sparse grids, the approach correctly identifies the largest valid square, whether it's a single cell or a larger square. This concludes the solution walkthrough for finding the largest one-bordered square in a grid. The time complexity analysis for this problem starts with the two main components of the algorithm, pre-computing the cumulative sums and checking for one-bordered squares. In the first phase, we calculate the horizontal and vertical cumulative arrays by iterating through each cell in the grid. These arrays store the count of consecutive ones horizontally and vertically for every cell, and since each cell is processed exactly once, this step runs in O(m*n) for a grid of size m by n. Now, in the second phase, we evaluate potential one-bordered squares. For each cell, we determine the maximum possible square side length by taking the minimum of the values in the pre-computed arrays at that cell. From there, we verify if a square of that size exists. The verification involves checking just two additional values in the pre-computed arrays, which are constant time operations. However, the while loop that performs this verification runs a number of iterations proportional to the side length of the square, which can be at most min, m, n. Since this process is repeated for every cell in the grid, the time complexity for this phase is O, m n min, m, n. Combining these analyses, the worst-case time complexity across both phases can be derived as O, m n min, m, n. When combining the time complexities of the two phases, we get O, m n from the cumulative sums phase, and O, m n min, m, n from the square checking phase. The latter dominates, so the overall time complexity is O, m n min, m, n. Now turning to the space complexity, the algorithm uses additional space for the cumulative arrays, horizontal and vertical, each of which has the same size as the grid, m n. This is in addition to the space required to store the grid itself. Therefore, the space complexity breaks down into O, m n for the input grid, plus O, m n for each of the two cumulative arrays. Adding these together, the total space complexity becomes O, m n, as it is dominated by these arrays. This efficient use of space enables the algorithm to handle larger grids without excessive memory overhead. To better understand the efficiency of the optimized approach, let's compare it to a naive solution. A brute force method would involve checking every possible square in the grid, and for a square of side length k, verifying the one bordered property would take O, k squared, operations. When extended to all grid cells, this results in a worst-case time complexity of O, m n min, m, n, 2. On the other hand, the optimized approach uses pre-computed cumulative sums to reduce the square verification step to O, 1. This improvement brings the overall time complexity down to O, m n min, m, n, which is significantly faster, particularly for larger grids. Looking at the best, average, and worst cases, the best-case scenario occurs when all cells are 0, allowing the algorithm to skip the square-checking phase entirely, leaving only the cumulative sums phase with O, m n, complexity. In the average case, the complexity remains O, m min, m, n, as it depends on the distribution of ones in the grid. The worst-case scenario, where all cells are 1, involves the maximum number of square validations, leading to O, m min, m, n, complexity, matching the theoretical bound. The time complexity of O, m min, m, n, can be mathematically justified by analyzing the two main components of the algorithm. First, pre-computing the cumulative sums involves iterating over all m n cells exactly once, which contributes O, m n. Next, in the square checking phase, we iterate through all grid cells once again, and for each cell, we may perform up to min, m, n iterations in the while loop to validate squares. This results in O, m min, m, n for this phase. Adding the two components gives the total complexity of O, m min, m, n, where the second term dominates. As for space complexity, the key contributors are the horizontal and vertical cumulative arrays, which are each of size m n. When combined with the space needed to store the input grid, the total space complexity is O, m n. The algorithm is thus both time-efficient and space-efficient relative to the problem constraints. When solving this problem, there are a few common mistakes that can derail your approach. First, not validating all four sides of the square is a frequent issue. For example, if you only check the top and left borders, you might miss gaps on the bottom or right sides, which means the square isn't valid. To avoid this, you need to ensure that all sides are properly checked. Another common mistake is using an inefficient brute force approach that repeatedly recomputes border checks for overlapping areas of the square. This redundancy increases runtime significantly, especially for larger grids. Additionally, incorrect handling of grid boundaries can lead to problems. If your algorithm doesn't properly account for edge cases, like when the square's size exceeds the grid dimensions, you may encounter index out-of-bound errors or fail to detect valid squares located near the edges. These issues highlight the importance of careful implementation and robust boundary checks. Now, another common pitfall is skipping dynamic programming optimizations. Without leveraging techniques like prefix sums or cumulative row and column sums, your algorithm might end up with a time complexity of n cubed, or worse, which can be impractical for larger grids. Using optimizations can significantly reduce the number of redundant computations and make your solution more scalable. Additionally, some people assume the grid is always square, when in reality, it could be rectangular with different dimensions for rows and columns. This assumption can lead to runtime errors or incorrect results. To perform well in interviews, it's essential to optimize your solution thoughtfully. For instance, use dynamic programming to pre-compute values like the maximum square ending at each cell. This bottom-up approach not only speeds up validation but also demonstrates a clear understanding of the problem. When explaining your solution, start with the brute force method to establish a baseline, discuss its limitations, and then show how you improved it. This approach highlights your problem-solving skills and structured thought process. This problem also connects to several related problems on LeetCode that you might encounter. For instance, LeetCode 1277 asks you to count square submatrices filled with all ones, while LeetCode 85 focuses on finding the maximal rectangle. LeetCode 221, which involves finding the maximal square, shares a lot of similarities with this problem as well. Additionally, LeetCode 304, which deals with range sum queries in a 2D grid, introduces useful preprocessing techniques like prefix sums that can be applied here. When it comes to alternative approaches, the brute force method is a straightforward starting point. It involves iterating through all possible squares and checking their borders, but the drawback is its n cubed complexity, which becomes inefficient for larger inputs. On the other hand, a dynamic programming approach can optimize this process. By using prefix sums or a bottom-up DP strategy, you can reduce the time complexity to n squared. This method is more efficient, but it does require additional space and careful planning during implementation. Another interesting approach is to use binary search on the size of the square. This method works by narrowing down the possible square sizes based on validation checks. The complexity of this approach is log min n m n squared, which can be advantageous for sparse grids where large squares are rare. However, the trade-off is that the implementation is more complex and requires a good understanding of how to combine binary search with grid validation logic. Overall, each approach has its strengths and weaknesses, so it's important to choose the one that best fits the constraints of the problem and the size of the grid. Great job! We've summarized the key points of the problem and walked through the brute force approach. Be sure to practice optimizing this solution and applying these concepts to similar grid-based challenges. Thanks for watching, and I'll see you in the next walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!